Hello everyone, I'm Paolo Franceschi and I'm gonna present this work about modeling physical human-robot interaction with game theory formulations in collaboration between the SUPSI, the University of Brescia, and the National Research Council of Italy. The main motivations to study and model physical human-robot interaction are that humans and robots have complementary skills, and some tasks require necessarily two agents, for example, large or deformable objects co-manipulation. The objective of this work are therefore to analyze behaviors of the human-robot dyad in a peer and leader-follower fashion, this with a view towards the role arbitration. The proposed method wants to model the interaction, particularly the physical human-robot interaction between a human and a robot, with a prescribed system. Game theory, in particular the differential description of the specific case, provides a model of strategic interaction among rational decision makers. In particular, in this work we focus on the cooperative and the non-cooperative cases. The low-level control is described by the impedance equation, and the human and the robot apply forces to such a system. So the question that arises is to model and define their control inputs UH and UR. By using the game theory, they can be modeled as the outcome of a game. Considering the non-cooperative scenario, the human and the robot, with their objectives, generates their control input regardless of the other's intentions, and they try to pursue their own objective. On the contrary, in the cooperative scenario, the human and the robot agree on a shared objective, and they work together towards that objective. The agreement happens by means of the parameter alpha, which represents a weight of their two objectives. In this work, we compare the cooperative and the non-cooperative models with a standard linear quadratic regulator. This is because, as we're gonna see, it turns out that solving the cooperative game theory problem is the same as solving an IQR problem, but they have different outcomes. I promise this is gonna be the only slide with some math, but it is necessary to understand the different problems. First of all, in the IQR case, the human and the robot have their own cost functions, they do not consider the opponents, and they solve two separate linear quadratic regulator problems with their objectives. In the non-cooperative case, an additional term couples the two cost functions. Therefore, also the two problems are coupled and the solution cannot be found anymore as with the standard linear quadratic regulators. Finally, in the cooperative case, the two players also knows the opponent's target and their objective also considers it. Indeed, in particular, in the cooperative scenario, the two players can agree by sharing a single cost function that is a weighted sum of the two individual cost functions. The choice of the weight alpha is part of the bargaining theory. This work arbitrarily selects the value of alpha to see how the system responds to different values. Note that by writing the cooperative matrices target, the cost function has the same shape as in the linear quadratic case, and so the solution of the cooperative problem is found exactly as a solution of the linear quadratic problem. So we made a problem conversion. To test the various models, we performed three sets of simulations, making variable the parameters that can be selected. Indeed, not all the parameters can be selected. The human one cannot be imposed, and they can only be recovered by experimental sessions. So we used inverse optimal control to recover the human weights on the cost functions. We performed simulations for three different cases. First of all, we made different values of alpha, and this is made because changing alpha, it moves the weight of the shared cost function from the human to the robot side, and it modifies consequently the shared target, the shared objective. We also performed simulation with small values of the robot state weight matrix QR. This means that the robot cares more about the human target rather than its own. And finally, we simulated the system response for different values of the robot's control weight matrix, RR. This makes the robot more reactive to pursue the goal. Here you can see the result for the first scenario with the different values of alpha. So the IQR case, which is represented by the dashed lines, is less affected by the change of alpha, since the other control input can be seen as an external disturbance. And in the IQR case, the robot just want to reject this disturbance. In the non-cooperative case, the dotted line, instead, there is a significant variation of the target. Notably, in the non-cooperative and the IQR case, both players keep putting effort when the equilibrium is reached, and this is because they are always against the human. In the cooperative game theory case, both players reduce their effort to zero after reaching the equilibrium point, because they reach a shared reference together, and no one wants to change it, because they agreed on it. Figures here plots only the cooperative game theory variations, since the other controllers have similar behavior to this one. Here we change the state matrix of the robot. On the left, you can see the variation of the state of the system according to various alpha, and it happens that by lowering the robot's with the robot state weight matrix. Because the weight on the robot reference is low, the state goes quickly towards the direction of the human reference, even for small values of alpha, with alpha greater than 0.1. In general, low value of the QR means that the robot would prefer to go towards the human goal. In this case, alpha is kept equal to 0.5, and we made variable the robot's control state matrix. With the cooperative formulation, the equilibrium position is constant for all the values of R, while the human and the robot control inputs vary according to this matrix. The effort of the robot increases as the RR increases, and vice versa for the human effort. Conversely, the IQR case and the non-cooperative game theory reach different equilibrium points according to the robot matrix. Finally, we computed the cost of the human and the robot incur with the various scenarios, and it turns out that it is very dependent on alpha. We also performed experimental test. The setup is visible on the left, with the human grasping the robot at its tip and the target shown on a monitor. Both have to reach a specific target that is different. The human only knows his own and the agreement parameter alpha. On the right, there are visible some results. As expected from the simulations, the cooperative game theory shows that once the equilibrium is reached, so the shared reference is reached, neither the human nor the robot puts any more effort into the system. On the contrary, the other two controllers still inject effort into the system to keep the equilibrium properly. Here you can see experimental results again. On the left, there is the measured human cost, showing that for low level of alpha, the non-cooperative description is more favorable for the human. On the contrary, for high values of alpha, the cooperative game is better, still from a human point of view. On the right, we are also measuring the error between the measured and the nominal control inputs of the human, to see which model is more reliable in describing the physical human-robot interaction. And it turns out that the cooperative game is the one that better fits with a lower error on the predicted effort. To conclude, with the proposed model, we can say that in the cooperative case, high values of alpha means that the robot tends to assist the human in pursuing his or her goal. This situation is sick when the human is leading the task and wants that the robot assist as a follower. On the contrary, low values of alpha, the robot expects that the human assist the robot itself, and this situation does not apply to real-world applications. It is very unlikely that the human knows the robot's objective and the human wants to put some effort into pursuing something that he doesn't care. In the non-cooperative and linear quadratic case, low level of alpha, the robot tends to pursue its own goal. This situation is desirable for some specific subtasks. For instance, when you are co-manipulating an object, during the manipulation everything is fine. In the end, you want to precisely position a large object, and in this case the robot should lead. Let me leave you with the target application of the models analyzed in this work. So we studied different models seeking for methods that allow role arbitration, so dynamically switch the leader-follower role during a task. And this can be achieved by dynamically switching from the cooperative to non-cooperative formulation of the problem according to the desired objective. Here you can see a bad quality video on possible target applications with the real industrial case scenario. Here the co-manipulation of large flexible objects is targeted. This requires very precise positioning at the end of the trajectory, with the robot leading and the non-cooperative model implemented to precisely reach the target objective, the target goal. Instead, it allows for trajectory modification during the transfer with the human leading and cooperative model implemented, so the robot can just follow during the co-manipulation and leading at the end. Thank you for your attention, and please feel free to contact me for any further questions.